Maxwell's first law. And before deriving the Maxwell's first law, we must know some basics. Now, first let's talk about what is an electric field. We have two charges, a positive charge and a negative charge. And the area after which the effect of this charge can be experienced is known as the electric field. Suppose we have kept a Q0 charge here, then this charge will experience a force because of this positive charge. Hence, this whole area is known as the field of this positive charge, whereas this area will be known as the field of this negative charge. Field is nothing but the area in which another charge can experience the force due to this charge. Suppose we kept a positive Q0 charge, then this charge, since it is kept in the field of this positive charge, hence this charge will experience a repulsive force. But if a negative charge would have been kept inside the field, then this charge would have experienced an attractive force towards the positive charge, because we know that two similar charges repel each other, whereas two opposite charges attract each other. Similarly, if we keep a positive charge in the field of this negative charge, this will be attracted, whereas if we keep a negative test charge, this charge will be repelled by this negative charge. Here Q0 is a very small charge which is used to test how an electric field will act on this small charge. And suppose if we keep another test charge outside of this field, then since this Q0 charge is kept outside this field, so it will not experience any force because it is outside the area of the electric field of this charge. Hence now we know that what does an electric field means. An electric field tells us about the force that a charge will experience if it is kept inside the area of the electric field of that charge, which may be positive or negative. Now, in order to derive the Maxwell's first law, we must know the difference between E and D. E means electric field, whereas D means electric displacement field. So right now we studied that what does electric field tells us. Electric field tells us about the force experienced by a charge placed in the field. Suppose this Q0 charge is placed in the electric field of this positive charge, then this charge will experience a force because of the electric field that is being produced because of this positive charge. And the force will be a repulsive force because these both charges are positive. And that force will be equal to this charge times electric field. This will be the force experienced by the test charge Q0. Now this electric field depends on the free charges as well as the bound charges. Now from where does the concept of these bound charges come from? Well, the concept of these bound charges. Bound simply means that the charges cannot move or are not free. This happens in case of dielectrics. A dielectric is something which, when comes in the effect of an electric field, suppose these were some normal plates, there is no charge right now and there is no electric field, but if we apply an electric field, then one part becomes positive whereas the other part becomes negative of these plates. Then these are called dielectric. No electron flows, but one side becomes positively charged and the other side becomes negatively charged. Hence, this arrangement is a polar arrangement in which one side is positively charged whereas other is negatively charged. These positive charges that have accumulated in this side of the plate does not move. These are called the bound charges. Free charges are those that will be moving here, right? But bound charges are those which are bound to the metal and cannot get out of the metal but will accumulate in the metal. And because of these bound charges, one side of the plate becomes positive whereas other becomes negative. Hence, the bound charges are created due to the polarization of the dielectric. Polarization means that one side becomes positively charged and the other side becomes negatively charged. And these are the bound charges in this dielectric. So while we are talking about the electric field, then we are considering both the free charges and the bound charges. And the Gauss law in case of electric field says that the electric field intensity, or from this side we can say that suppose we have a surface, then total electric flux, suppose these are electric field lines passing through this surface, then this electric field lines must be proportional to the charge. Why this must be proportional to the charge? Because total electric flux flowing out of surface must be proportional to total charge enclosed inside the surface. Why are we saying so? We are saying so suppose we have this cylindrical type thing and the charges are moving outside. Then these charges, those are moving outside. Then we can say that what is flowing outside must be present inside. Hence, the electric field that is coming outside of these charges must be dependent on the charges. These charges, they are coming out of this. Hence, we say that electric field is directly proportional to charges, and we put an surface integral in order to calculate the total electric flux coming out. Hence, we get something like this is proportional to the charges. And in order to put an equal sign, we put a constant of proportionality, that is mu naught. Hence, this is the Gauss's law in case of electric field. But this electric field becomes complicated in case of a dielectric because bound charges also contribute. Then what is D? D is electric displacement field. It is a type of field introduced to simplify the problems in the dielectric. In the case of the electric displacement field, we ignore the bound charges. The dielectric is actually equal to this expression where P is the polarization vector. We understood that polarization means one thing becomes positive, another becomes negative. And since we only consider the free charges in case of the electric displacement field, and hence this expression is similar to this expression, but there is no constant. Here we have the surface integral of D, which is equivalent to the free charges only, and there are no bound charges, whereas here this Q total means bound charges plus free charges. Hence, electric field takes into consideration both free charges and bound charges, whereas D is also electric field, but it is the electric field produced only because of the free charges. Hence, this is the difference between an electric field and electric displacement field, and the relation between displacement and electric field is something like this. Hence, this can also be written like this: the surface integral of the electric field, which is equivalent to Q total, where Q total is equivalent to the free charges and the bound charges, whereas for the electric displacement field we have this expression which only includes the free charges. Now we can simply derive the first equation of Maxwell. The first equation of Maxwell is that it says that divergence of electric field is equivalent to rho upon epsilon naught. Here E is the electric field, and here rho is the charge density. Now suppose we have a container and this is the surface, and suppose the charges are coming outside. Suppose we have positive charges, so positive charges are coming outside, So an electric field must be produced, which is also moving outside. Hence, the total electric flux that is coming out of this surface can be summed up as this. We take the total electric flux coming out of this surface S. So this integral adds up all the electric flux that is coming out of this surface, which is equivalent to, we know that this is proportional to the charges. Hence, it is equivalent to the charges inside that are coming out, because electric field is producing because of these charges only. Hence, we can write Q enclosed, or the charges which are inside, these are Q enclosed upon the constant. Now, while we were studying equation of continuity, we learned that suppose these charges are coming outside of this volume V, then these charges can be written as rho, where rho is the charge density, which represents the sum of all, or the effect of all these charges. Then this can be written as, for this volume, we can add up all these charges as like this. So all the charges that are present inside this volume can be added up like this. Hence, the Q enclosed, the total charges inside, can be written like this. Hence, this equation can now be written as like this. Hence, on the left hand side, we have a surface integral, and on the right hand side, we've got a volume integral. Now, we can use the divergence theorem to convert this surface integral into a volume integral. Now, according to divergence theorem, we will simply take the divergence of this thing, and this whole thing will convert into a volume integral. Hence, divergence of E gives us the volume integral. Hence, this left hand side, this surface integral, we converted into volume integral using the divergence theorem. Hence, since this integral are same on both the sides and we can compare these things, hence we've got our first Maxwell equation, which shows that divergence of electric field is equivalent to the charge density divided by the constant. Now, what is the physical significance of this? We know that divergence, this thing is divergence. It simply means that there is some source or sink present. What do I mean by source or sink? Now, suppose we have this fountain. Now, since the water is coming out of the fountain, this thing is acting like a source, since something is coming outside of it. Whereas in kitchen we have sink. As the water comes out of the tap, this water gets inside this sink. Hence, we have two things. We have a source and a sink. Source is something which gives out something, or out of which something is coming out, whereas a sink is something into which something enters. And this is what this divergence thing tells us. Hence, the left hand side means divergence of electric field. This means that there is some point into which either an electric field is entering, or there is a point out of which an electric field is coming out. So electric field, if it is entering somewhere, it is acting as sink, whereas out of which is coming out is acting as source. And we know that suppose we take the case of source, then the electric field is coming out. Since this is a source, so electric field is coming out. And we know that suppose there must be some positive charges inside. And since there are positive charges, hence the electric field is coming outside of this place, where these all positive charges can be represented as rho. Whereas in case of sink, where the electric field is entering in, there must be negative charges inside, and this group of charges can be represented as a rho. Hence, in this case, we get that the divergence of electric field is equivalent to rho upon epsilon naught, where rho were the negative charges. Hence, this law of Maxwell simply tells us there exists a sink or a source out of which an electric fields come out or enter. It simply shows that positive and negative charges exist in this universe, and this equation confirms that. Now another way to write this equation is like this. Now how do we derive this equation? Above we studied that the surface integral of d is equivalent to q free, whereas we studied that in case of electric field it is something like this. So here we've got this expression that we studied above, where d refers to the electric displacement field that only depends on the free charges. Hence we know that q can be represented as rho dv. We have already studied this, so we can simply put rho dv in place of this. Hence we get something like this. Replace the charge with this. Now simply by using divergence theorem again, we will convert surface integral into volume integral. Hence we get something like this. And since both the integrals are same, hence we can compare the terms inside. Hence we get divergence of d is equivalent to the charge density. This also explains the same thing. This shows that this electric displacement field, in case of positive charge, the electric displacement field must be coming outside of something, and in case of negative charges must be entering inside. And divergence tells about if it is entering inside or if it is moving outside, or simply if there is a source or a sink for this electric displacement field. And it is equivalent to rho because it is these charges, these a lot of charges rho, which may be negative in total or positive in total, that are causing the electric field to either come outside of that place or enter into that place. Hence, this is the physical significance of the Maxwell's first law and their derivation.